Now that we have an idea about the structure of energy levels within molecules, I want to spend a little bit of time talking about how we might look at the population of those energy levels by the molecules in a system. And in particular, we're going to be interested in the statistical characteristics of the molecules as they form a distribution for that. So let me remind you that we're talking about a distribution of molecules that will use in terms that will characterize basically by the number of molecules that are in each of the various molecular energy states. So maybe I'll make that N sub J. All right, so this is the distribution that we're interested in. And the whole idea is that we're going to want to maximize this distribution. We want to find the distribution that has, if you will, the most space for molecules. Now, there's a couple of key points that I want to make before I jump into this. All right, so let me label that key points. As energy increases, so this is increasing energy, there's a couple of things that happen. All right, one of these is that the levels get closer together. So as we go higher in energy, we find that there are more and more energy levels available. So the next small step up in energy is more likely to encounter more energy levels. The other thing that happens as we go higher in energy is that the degeneracy, and remember we use this to talk about the energy levels of a molecule in terms of the degeneracy is really the number of different ways you could partition the internal energy of a molecule among its translational, rotational, vibrational, and electronic degrees of freedom. But the degeneracy increases as we go higher in energy. So the more energy that we're going to have in a molecule, the more possible ways there are of putting that energy into the molecule. Now, I want to specify also that the distribution is something that tells us basically how many molecules are there that have energy E sub j. So distribution specifies the number of molecules that are in energy level E sub j, where I'm using this funny E to indicate the energy levels of a molecule. But there are many ways that we can achieve that energy, okay? And that's what really is the meaning of the degeneracy in this case. So there are many ways to do this. A separate consideration, though, is that there are many ways that we can take a given distribution and populate it. So many ways to populate a distribution using indistinguishable molecules. So if we don't have labels on the molecules, and in practice we don't, then we have to be aware of the fact that there are many different ways that I can place the molecules in those different slots. And so this is what's going to contribute to this concept that we identified last time as the microstates that are available. So the distribution itself represents a macro state, and it basically says something about the state of the whole system. The microstates are really the little individual ways that the system can achieve that macrostate. So if all of the microstates are equally probable, then the particular distribution that has the most microstates is going to, by default, be the most probable one. So let me illustrate this with a quick example. Let's suppose that I have a simple system and I've got 3 energy levels in this system. I'll call those little e1, little e2, little e3. And let's say furthermore that I've got 1 molecule that's in E1, I've got 2 that are in E2, and 1 that's in E3. Now I'm going to go a step further and say, at least for the time being, that I can label those molecules. I'm going to label them A, B, C, and D so that I can keep them straight. Now what I want to know is how many different ways can I populate this distribution with these 4 molecules. All right, well, I could have A here in the very first one, and then I could have B and C in the next one, and D in the top one. Or I could have, again, A in the bottom one, and have B and D in the next one, and C in the top one. Or I could have A in the bottom one, I could have C and D in the next one, and B in the top one. So basically I've identified 3 different ways that I could populate these energy levels with these 4 molecules, but all of them have A in the lowest level. So I hope it's going to be easy for you to accept that I have 3 that have A in the lowest level, I'm going to have 3 that have B in the lowest level, I'm going to have 3 that have C in the lowest level, and I'll have 3 more that have D in the lowest level. So when I add all these up, it turns out that I'll have 12 different ways that I can populate these energy levels in this distribution. All right, so this would represent, in some ways, at least at this stage, this would represent 12 microstates, or ways that I could ways that I could distribute these things among them. Now, another thing that I want you to notice is that there's an easy statistics formula that one could use to do this. I've got 4 molecules, so as I assign them to slots, the first molecule has 4 different slots it can go to. Okay, so the next one would have 3, the next one would have 2, and the last one would have 1. But I'm going to be overcounting this, okay, because in the middle one here, it doesn't matter whether I put C in first or B in first. As long as I put them both in the middle one for this particular distribution, I would get the same result. So in fact, I have to divide this by 1 times 2 times 1 times 1. So the statistics formula that most of us learn in school is that this would be 4 factorial, that's 4 times 3 times 2 times 1, divided by 1 factorial, 2 factorial, 1 factorial. Okay, this little exclamation point is a factorial. All right, now notice that this is telling me how I parcel those molecules out into the 3 different energy levels. All right, so this formula is a fairly safe one. It's one that we learn in basic probability and statistics at an early point. Now, at this point, I could say, if this is all there was to it, that if I could easily generalize this now, that if I had a total of n, big N molecules, and I'm going to parcel them out as N1, little n1, little n2, little n3, as I'm done up here in the distribution, that this would result in a total number of microstates that would look like this: n factorial divided by little n1 factorial, little n2 factorial, and so forth, little nj factorial, and so on. All right, but I'm going to put a question mark here because we're not really done just yet. All right, let's suppose that I have degeneracies. So let's suppose E1 just has a degeneracy, G1 is equal to 1. Let's say that energy level E2 has a degeneracy of 3, and energy level 3 has a degeneracy, let's make it 6. Okay? So now as I'm plugging molecules into these energy levels, I have multiple choices of states that they can go into. All right, so it's not just plugging, say, 2 molecules in here. They now have multiple options of where they can go. Okay, now this one, remember, has N1 is equal to 1, and this one has N2 is equal to 2, and this one has N3 is equal to 3. Equals to 1. I got a little carried away there. All right, well, this one's the easiest one, the top one, because I've got 1 molecule, I've got 1 space to put it. There is one way to do that. All right, this one is a little bit more complicated because each of these 2 molecules here has 3 different possibilities. So in fact, what will turn out is that I have 3 possibilities for each of the 2 molecules. So I have a total of 9 ways that I can put them in there. And that includes putting them both in the same degenerate state or putting them in 2 different degenerate states. All right, down here again, I have an easy one. Even though I have 6 slots, I only have 1 molecule, but now it has 6 choices. So in fact, it could go in any of these 6, and it doesn't matter. They're all equally possible. So I have a total of 6 choices there. So when I put all these together, I've got 1 possibility here, I've got 9 here, I've got 6 here. that would suggest that I have a total of 54 possible ways of putting these molecules in when I add this concept of degeneracy to the factor, as opposed to the 12 that I got from my initial thing. Now, in fact, we would multiply these two factors by each other because each one of these 12 has 54 different ways that it could be populating those states. All right, but I hope you'll forgive me for not going into a deep explanation of this, but we've in fact overcounted. And the way that we've overcounted is that, in fact, molecules can't be labeled with A, B, C, and D. In fact, we don't know which one is which, so we have to correct for that overcounting. The simplest way to correct for that overcounting is to say that we're going to divide by n factorial times this formula that we've gradually built up here, and this will cause our distinguishable particles to become indistinguishable. Now, I will also mention that this is an approximation, given the way we've set this up, that in fact it's a little bit more complicated than this, but this is a good rough way to go from having distinguishable particles to indistinguishable. Now, the last thing I need to do is figure out what was the formula that was going on here among the degeneracies that led to these different factors. Well, I think for the first one and the last one, this is pretty easy. It was just the number of degenerate states that I had to choose from. But what about this middle one? Well, I had 3 degenerate states and I had 2 particles, and I ended up multiplying 3 together twice. And it turns out that the factor that I'll get out of this is the degeneracy of the state raised to the power of the number of molecules that are occupying that state. So in fact, my total number of microstates at any given point is going to be, I'm going to correct for indistinguishability here, and it's going to be now my n factorial over n1 factorial, n2 factorial, and so forth. And it's going to be times the degeneracy of each of these levels raised to the power of the number of molecules in it. So in fact, I've got to multiply by all of these, so I really should have a product sign in here telling me that I'm taking the product over this. So I haven't written it very well, but let me write it again in red so that it will be in a good format for you. All right, this will be essentially, and I'm going to cancel these big n factorials out. So the total, the ultimate final number of microstates is going to be the degeneracy of each state raised to the power of the number of molecules in that state over the number of molecules factorial, and then I've got to product over all the possible molecules, all the possible states in the system. So this is the working formula that we're going to have for calculating the number of microstates that go within a given possible molecular distribution.